As we talk about double integrals, so integrating functions with multiple independent variables, we want to keep in mind that all of our previous rules and theorems related to antiderivatives and integrals still apply. So we can integrate our basic functions in the same way. The substitution method still works, integration by parts if we were to have to consider functions that complicated. So all of those previously established rules and properties still apply to finding integrals and antiderivatives for these multivariable functions. However, we need to make sure when we're looking at these problems, we're paying close attention to the variable that we're integrating with respect to. So, for instance, if we have some given function, f of xy, we could write the integral of that function, dx, which prior to considering double integrals and partial antiderivatives, we always just sort of tacked on this dx notation without maybe giving a lot of consideration to what that means. What that's telling us is which variable to integrate with respect to. So if this is a dx, then we would want to integrate the x variable and treat y as a constant. Similarly, if we have some given function, f of xy, we could integrate that function with respect to y by putting a dy notation at the end instead of dx. So what this would mean is we would treat y as the variable to integrate with respect to and treat x as a constant. So we always have one variable we're integrating with respect to, and the other variable is treated as a constant. So these are still just single integral statements. What we're going to look at more in this section will be the idea of double integrals, meaning we'll start off with the integral of some function f of x sub y, and say we would first perhaps differentiate with respect to x, and then have a second integral statement where we would integrate with respect to y. So what we would see is the double integral sign, our given function, dx dy. To approach a problem like that, what we would do is basically think of these as sort of acting like parentheses. We would want to start from the innermost expression and work our way out. So the first thing we would do is integrate this expression with respect to x. Once we get that result, then we would move on to integrating with respect to y. A similar statement could start off as integrating f of xy first with respect to y, and then with respect to x. So the difference between these two statements is the order of the integration, whether we first integrate with respect to x or first integrate with respect to y. The other thing that we'll be adding to these statements then is an upper and lower bound for definite integrals. So if we were integrating with respect to x from a to b, again, the first thing we would do is evaluate that interior integral, integrating with respect to x from a to b. In the second expression we have here, it would be our last step to integrate with respect to x, since that's the outer integral. We would evaluate that from a to b. And if we want to integrate with respect to y from c to d, in the first expression that would be our last step. In the first expression, that would be our first step. But what we would find is that these two results would be exactly equal. So the order of the integration doesn't matter. We can integrate with respect to x first or with respect to y first when we're evaluating these double definite integrals. But what's going to be important is to make sure we're keeping the correct upper and lower bounds associated with the correct variable we're integrating with respect to. So if first we're integrating with respect to y, we need that interior integral to be the upper and lower bounds for our y variable. And if first we're integrating with respect to x, we need the upper and lower bounds to be the upper and lower bounds for our x variable.